both parts available later on. Share the screen. Okay. Do you see the chapter 4 notes there?
Yeah, they're up for me.
Okay, that's good. A couple of things here. All right. Okay, so we've got motion in 2 and 3 dimensions. So you can see all of our objectives. All right, so now what we're going to do is we're going to talk about position and displacement and all of that gobbledygook that I had mentioned in chapter 3 regarding vectors. Well, here's where it comes into play. We're going to talk about a position vector. And basically what that does is it locates a particular particle in space and gives you the dimensions that you have to travel in order to be able to get there. So, for example, you've got your I, J, and K magnitudes. You plug them in, and that gives you your position vector. So if you were to take those and you were to plug them in, here's your coordinate axis. You got X, you got Y, and you got Z. So you move -3, and then you move up 2 in the Y direction, and then in the Z direction, you're going to move 5. This is where it puts you. Your origin is here. That's where you started. And this is your resultant vector of all of those moves in each component direction. Obviously, the change in the position vector is going to be considered to be a displacement. So if you subtract the two, your change in your position, or the change in the resultant vector, is going to be the difference of your second vector minus the first. And you're going to do that for each direction. So you've got x2 minus x1, y2 minus y1, and z2 minus z1. If you want to simplify the way it's expressed, you can use change in x, or delta x, delta y, and delta z. So if we're going to look at the average velocity, what we're going to be looking at is the change in the displacement over the change in time. Another way that you can write that is going to be the change in x, change in y, and change in z, all of that divided by time, or the change in time. So you've got an example here. Particle moves through displacement of 12 miles in the x direction and 3 miles in the y direction in 2 seconds. So you take the average velocity and you take the change in your displacement, and then you divide it by the change in time. Obviously, you're going to start time at 0 seconds, so wherever you stop it, that's going to be your change. You do the division, and then you come out with 6.0 meters per second in the x direction and 1.5 meters per second in the y. The instantaneous velocity. If you're looking for something at a particular point, if the other way you can look at it is the limit of the average velocity as the time interval shrinks to 0. Those are your limits in the calculus course. So the instantaneous velocity is going to be the derivative with respect to time of your displacement vector. So the visual displacement and instantaneous velocity. So you've got R1 here, and then you've got R2 there. This is considered to be your displacement. as the particle moves, the position vector must change. And then the velocity vector is always tangent to that particular path. And you can see here the x and the y components of the velocity along that particular path, or at least at that particular point. So the direction of the instantaneous velocity of a particle is always tangent to the particle's path. So if you want to write this in unit vectors, you're going to take the velocity, which is going to be the derivative with respect to time of x, y, and z. And then you can also take that derivative and split it out among the component vectors. Once you do that, the derivative of x with respect to t, that's going to be called the velocity in the x direction. So you're taking this and replacing it with this. Same thing holds true with y as well as z. So our first checkpoint. So we've got a figure here that shows a circular path taken by the particle. If the instantaneous velocity of a particle is going to be 2 meters per second in the x direction and a minus 2 meters per second in the y direction, through which quadrant is the particle moving at that instant if it is traveling clockwise and counterclockwise around the circle? If it's traveling clockwise around the circle, it'll point that particular direction. If it's counterclockwise, it'll be pointing that direction. Acceleration. Your average acceleration is building on the same definition that we had for the average velocity. So we're going to take the average acceleration and define that as the change in the velocity divided by the change in time. Your instantaneous acceleration is going to be as the limit goes to 0, or as the limit as t approaches 0. You're going to get the same type of math here where you go the derivative with respect to time of each of the velocity components. As you do that, you will see that you've got ax, ay, and az. So you've got your path here, and you've got your particle that is accelerating along this particular path. You can see the direction out this way, and if you define your coordinates such that this is x and this is y, and you've got your components of the acceleration vector at the particular points. So here are 4 descriptions of the position in meters of a hockey puck as it moves in an XY plane. So are the x and y acceleration components constant? Is acceleration constant? Well, let's take a look at the first part. What would be, and I'll give you a hint, these are going to be the answers. Is the acceleration constant in the x direction here? How would we determine that? We would determine that by taking the derivative of the function, so dx dt is going to be equal to, and maybe you can tell me what the derivative is of that particular function. The first derivative with respect to time. Have you gotten to the chain rule yet?
I think we talked about it a little bit, but after the couple months of COVID, I just got to write this down. So
okay, that's fair enough. Chain rule for polynomials, I'm going to take the exponent, multiply it by the coefficient, and then reduce this exponent by 1. So this will end up being minus 6t. And if I do the same thing for the second term here, that t ends up disappearing. So it becomes minus 6t plus 4. I want to compute the second derivative. I'll take the derivative of this derivative. That ends up being minus 6. Would we consider minus 6 to be constant?
Yeah, that seems constant.
Yes. So our answer, as far as the component, the AX component for this, yes, it would be constant. What about here? The dy part. Well, let's kind of work through that. Derivative of y with respect to t is going to be 12t minus 4. Take the second derivative. Should end up with just 12. So that also would be considered constant. So the derivative of both of those, if we're the second derivative of both of those, would end up being constant. Because of that, the acceleration is constant. If we were to take the second derivative of this, we would find out this is our function. Second derivative is going to end up being minus 18t. Is that considered to be constant?
I'd say no.
And you would be correct by saying no.
Yeah, that's good.
If you take the second derivative of this, you would find out that it would be constant. However, if it's asking if the vector of acceleration is constant, the answer in this particular case would be no, because the x component of it is not constant. If both components are constants, then yes, it would be. And that's what the question here is asking. Okay, projectile motion. So, projectile is defined as a particle moving in the vertical plane. It's got some initial velocity, we're not sure exactly what it is. And the acceleration is always going to be free fall acceleration. In other words, it's always going to be the force of gravity, which is going to be minus 9.8 meters per second squared. So the motion of a projectile is projectile motion. Looks like a big shock there. If you're launched with an initial velocity, then your velocity vector can be written with components. The velocity, the x component of the velocity is basically going to be your magnitude here times the cosine of the angle and the y is going to be along the same lines except using sine. What you're also going to find out in projectile motion is that the horizontal and the vertical motion are independent. One does not influence the other. Because one does not affect the other, we can take a two-dimensional motion problem and turn it into two one-dimensional problems. Work with the x's and then the y's. So let's take a look here. At a certain instant, a fly ball has a velocity of 25i minus 4.9 j hat. The x-axis is horizontal and the y-axis is upward. So, has the ball passed its highest point? In this particular case, we would say yes, because what's happening, is the ball rising or is the ball falling? According to that vector definition.
According to the vector definition, wouldn't it be falling?
That's right. It's falling because the j component is negative. Had the j component been positive, then the ball would have been still rising, which means it would not have passed its highest point. So for horizontal motion, there's no acceleration. The reason for projectile motion that there's no acceleration in the horizontal direction is there's nothing pulling it and there's nothing pushing it. So the velocity is considered to be constant. These equations are going to come out of, I believe it was chapter 2. So that's worth a refresher. This comes from what we had established earlier of the component of the velocity vector falling along the x-axis. If you'll also go back to chapter 2 and you'll look at the equations, 11, 15, and 16, what you will find is that for a projectile motion, we're going to take A and we're going to replace it with minus G. So the equations are going to look very much the same. It's just the positive A is now turned to a minus G. So a projectile's trajectory is going to be its path through space. It should trace a parabola. And it's found by eliminating time between equations 4.21 and 4.22. So if you take this and this, basically if you take this, solve for t, and place it into this, you'll end up finding that this will describe its path through space. At the very least, well, it's got both the y and the x components in it. The horizontal range is going to be the distance the projectile travels in x by the time it returns to its initial height. So in other words, this is as far out as it's going to be able to reach in the x direction. So the horizontal range is going to be the maximum for a launch angle of 45 degrees. If you look at the definition there, that's it's taking the sine of 2 times the angle that's made. That's the longest range that you're going to be able to produce. So in projectile motion, we're going to assume that air resistance or drag is considered to be negligible. In other words, we're going to ignore it. As you can see here, in a lot of situations, if you choose to ignore it, you can, but your results are going to pretty much not match up with reality. But for the sake of these computations, we're just going to go ahead and assume that. So we've got 2 fly balls here. We've got the path in air and then the path in a vacuum. Would you argue, with looking at the differences between these, that air resistance is not negligible?
Yeah, looking at the differences,
Yep.
air resistance does play a big part.
Mm-hmm. Yep, it does. Matter of fact, here's a graph of that particular motion. So you can see here, this is with air resistance, this would be in a vacuum. So we got a fly ball, and it's hit into the outfield, and during its flight, ignoring the effects of the air, what happens to its horizontal and vertical components of the velocity? And then what are the horizontal and vertical components of its acceleration during the ascent, during the descent, and then at the topmost point of its flight? So the part A, what happens to the horizontal component of velocity? What that's asking is what's happening in the x direction. In the x direction, if we're ignoring the effects of air, there's nothing there to slow the velocity. So the velocity in the x direction is going to be considered to be unchanged. The vertical component of the velocity, however, is always going to be decreasing. Why would that be the case?
Because gravity.
There you go. Gravity. Gravity is going to be affecting the velocity. It's always going to be decreasing the velocity in the y direction. What is the horizontal component of the acceleration? Well, that's asking what the acceleration in the x direction is going to be. And the acceleration in the x direction is going to be 0 because we've got nothing that, if we're ignoring the drag component here of air resistance, if we have that going on, we've got nothing slowing down or trying to accelerate the ball. So it's going to be considered to be 0. For part D, the vertical component of the acceleration is going to be the effect of gravity at all times. Gravity is going to accelerate it, and it's going to accelerate it downward. All right, uniform circular motion. This is something that can confuse quite a number of people. But what we're talking about here is a particle that travels around a circle or a circular arc at a constant speed. Now, what's happening to the vector component as the ball or the particle is moving around in a circle? Is the velocity staying the same as it's moving around?
Would it? Because I mean, would it stay the same or?
Okay, don't confuse velocity with speed.
Oh, you're right. Yeah, because velocity has direction.
Right, it's got the direction, and that's the part that can sometimes trip people up. It even tripped me up the first time I went through this. And because that velocity vector is changing, what is the particle doing? It's accelerating. So velocity and acceleration have a constant magnitude. In other words, it's the same, then it's traveling at the same speed, but the direction is always changing. And if you look at that diagram, you can see that the velocity of the particle is always tangent to the motion around the circle. What's really wild about that is that not only is the velocity vector tangent, look at the acceleration. The acceleration is pointed inward. Now that's an odd, feels like an odd description of what's going on, but that essentially is how we're describing uniform circular motion. So acceleration is called centripetal acceleration. Centripetal, if you take the word and pull it apart, it's center seeking. It is directed radially inward. And if you look at acceleration as it's defined, it's v squared divided by r. The time it takes, or the period that it takes to go all the way around the path exactly once, is going to be 2 pi r divided by v. And that kind of makes sense. In other words, your path, it's distance divided by the speed, or the velocity in this case. So we've got an object that moves at a constant speed along a circular path, centers at the origin. When the object is at x is equal to minus 2 meters, its velocity is minus 4 meters per second in the y direction, minus y direction. Given an object's velocity and give the object's velocity and acceleration at y is equal to 2 meters. When y is equal to 2 meters, basically it's gone. If I were to draw a circle here, we've gone from this point on the circle up to here. So if the velocity is going to be minus 4 meters per second in the j direction, up here, it's moving at that same speed. It's just the direction in this particular case is going to be pointed this way. So it'll be minus 4 meters per second in the minus I direction. If we're going to be looking at the acceleration is going to be pointing in this way. Let's see, I don't see exactly where they've got. Okay, so the acceleration, what am I missing here? V squared over r, that's what I'm missing. We know the acceleration is at 2 meters. Yeah. It's going to be v squared, which we decided was minus 4. Meters per second. It's going to be squared divided by r, which in this particular case is going to be 2. So that's going to be 16 divided by 2, which is going to be 8. However, we have to take into consideration the fact that the acceleration in that circle that I drew would be pointed down in the j direction. So the answer would be minus 8 meters per second squared. Okay. So measures of position and velocity depend on the reference frame. So how is the observer moving? And our usual reference frame is that of the ground. In other words, it's not moving. So we're going to read the subscripts listed here as P measured by A, P measured by A, P measured by B, and B is measured by A. Frames A and B are each watching the movement of object P. So you've got this reference frame, and then you've got this reference frame. And so frame B is moving past frame A while we're both watching this particular point. So you've got this reference frame that's moving, we're watching this. This is just sitting still, it's also watching this. So if you want to relate your position in different frames, then let's see if I can get those all on the same. See if I can get that to stop coming down. I can't. Let's try this. There we go. So the X position of P as measured by A is going to be equal to X as P is measured by B plus X as B is measured by A. That's going to be kind of a, perhaps a tough thing to see, but if you go all the way out here, measuring that, then basically you're having to measure X as P is measured by B, and then you're also measuring this X difference as well. So this distance is going to be the same as from here to here plus here to here. That's what this is attempting to say. If you go through and you take the derivative, you can see that the velocities are basically the time derivatives of each one of those. If you go through and you take the time derivatives of the velocities, then you find the accelerations. Now, what you're also finding here is the accelerations for the non-accelerating reference frame. In other words, B is measured by A, that's going to fall away to be 0. That's where the acceleration as P is measured by A is going to be the same as P is measured by B, if they're non-accelerating. Once one frame starts to accelerate in reference to the other, then things get far more complicated. So observers on different frames of reference that move at a constant velocity, non-accelerating, relative to each other, will measure the same acceleration for a moving particle. So for frame A, you've got X is equal to 2 meters. You've got the velocity is equal to 4 meters per second. Frame B, X is equal to 3 meters and the velocity is equal to -2 meters per second. So P as measured by A, if you're looking at that, it's going to be 5 meters. V as P is measured by A, it's going to be 2 meters per second, and the acceleration is going to be 1 meters per second. If you go through and continue on and do the math, you can see all of the computations made here. So if we're still looking at relative motion in 2 dimensions, basically what we're going to do is we're going to take what we saw in the last section and we're going to apply it to another dimension, and we're going to have the two summed going at the same time. So positions in the different reference frames, we kind of saw that earlier. It was just along a number line, but here now we're going to add it in as vectors. Velocities, basically you're replacing R with a V. Accelerations are going to be a little bit different. You might think that this would carry over to the acceleration, but if the frames are moving at a constant speed relative to each other, then the acceleration for P as measured by A is going to be equal to the accelerations P as measured by B. So you got reference frame A, reference frame B. They're both observing the motion of P. These are how the vectors all match up. Non-accelerating reference frames are a little bit easier, I think, once you have a little bit of practice with it. Most of what I have here for the rest of this is just a summary of everything that we have gone over. It's kind of a lot to crunch into one night. Do you have any questions at this point?
Not really. I just know that I'm probably gonna like look over this again, and I just need practice with it.
Practice is going to help, because the more you apply it, the more you see how twisted and evil some of these concepts can become.
Yeah.
So, yeah, well, I'm sorry we didn't get Giselle back. But hopefully the information here is something that you can go back over and review. And then if you've got any questions, I'd noticed your post out there on the muddiest point. I might try to go through. I don't know if there's anything specific about that you would like clarification on, but I can try to dig up some other material there that might help.
Okay.
So if everybody could post something out there, and even if you don't have anything, if really you didn't have any issues or anything out there, and you just want to put I didn't have any issues, that's fine. It's
Okay.
just it's an easy few points for you to earn, just to have something out there, and it can also be something that the class can discuss.
Yeah, I can definitely like mention that to them because I have them in 8 a.m. class every single day.
Okay. But yeah, it's really an easy way to earn some points.
Yeah.
So, all right. If you don't have anything else, that's all I pretty much have for tonight. I will post these later on tonight, and then if you have any further questions as we go along, then just feel free to ask.
All right, sounds good.
Okay. All right. I appreciate you attending.
Yep.
All right. Have a good night.
You too.